Hello and welcome everyone. I'm Shah Faisal, Coordinator of Professional and Educational Activities Subcommittee, IEEE Power and Energy Society Young Professionals. And this webinar is brought to you by Professional and Educational Activities Subcommittee, IEEE Power and Energy Society Young Professionals. Today, our respected guest speaker is Dr. Farzaneh Bagheri. Dr. Farzaneh is Assistant Professor in Department of Electrical and Electronics Engineering, Antalya Bilim University, Turkey. She is an IEEE member. She is expert in the field of control and applications of power converters, energy conversion, and energy management of renewable sources. Today, she will talk about the application of sliding mode control method for power electronic converter systems. I would like to welcome Dr. Farzaneh for further discussion on the topic. Please, Dr. Farzaneh.
Okay, yes. First of all, I should thank you for organizing such a presentation. It's nice to be with all of you here and talk about my own field of study, and I hope that it is interesting also for all of you. So welcome to my presentation. My presentation is about the application of the sliding mode control method in power electronic converters. I'm Farzaneh Bagheri from the Electrical and Electronics Engineering Department of Antalya Bilim University in Turkey. So what we will see in this presentation, first of all, I would go through the principles of the sliding mode control. What is the sliding mode control? How to design it? How to assign a control rule? And also we will talk about the stability analysis of the sliding mode control method. Then I will tell you that why we use sliding mode control for power electronic converters, why it is interesting to use such a nonlinear method for power electronic converters. I will clarify this idea by an example of a rectifier. Then I will talk about the pros and cons of the sliding mode control method, and I will talk about the disadvantages of this method, and I will analyze the chattering phenomena. And then I will talk about some chattering alleviation methods. And finally, we will go through our goal, which is talking about the applications. What are the applications? We have different applications, but here in this presentation, I will talk about the DC-DC converters, two examples, the buck converter and dual active bridge converter. Then I will talk about the grid type inverters and about the quasi-Z source inverters. So let's go through a very simple example to clarify the sliding mode control method. It is a very simple system, a second order system, single input, single output. It means that we have only one input, we call it U, which is the control input of the system, and we have one output, which is Y, the control output of the system. And we have one state variable, and it is X of T. So here I have a second order equation. It is the mathematical model of an example system. The second derivative of X is equal to F plus G times U. And the output of the system is Y, which is considered to be equal to X. So let us consider that this system is a nonlinear system. It means that F and G can be nonlinear. And another important thing is that F and G are not known values. It means that we have uncertainty in such a system, but F and G are limited functions. It means that they are less than a limited constant value, F naught and G naught. So for such a system, we can use conventional control methods, linear control methods, nonlinear control methods. But right now, I want to tell you that why a sliding mode control method is the best method for controlling such a nonlinear system that has uncertainty inside. So what is our target? Our target is to control or tune the output value, which is YT, to track a reference that is Y reference. So it means that if I define an error, which I call it E, which is equal to Y minus Y ref, I like to make this error equal to 0. We have two steps in the sliding mode control method. The first step is defining a sliding function, which I call it S. This sliding function in a conventional sliding mode control method is a function of the error, derivative of the error or second derivative of the error, and it can be continued. So in the conventional sliding mode control method, we will use such a function which shows that S is equal to derivative d over dt plus a constant value which we call it c to the power of k times error. So what is k and what is c? K shows the power of this value, and it is equal to r minus 1. R is the relative degree of the system. So it means that in a conventional sliding mode control method, when you want to define the sliding function, you should know the relative degree of the system, and then k should be equal to r minus 1. So what is the value of c? C is the coefficient, positive constant value. We call it the gain of the sliding function or the coefficient of the sliding function. So let us go through finding the value of k and some examples of the sliding function. For example, if k is equal to 0, our sliding function will be equal to e because k is equal to 0, so s is equal to e. And if k is equal to 1, then our sliding function is d over dt plus c times e, which means that we have e dot plus c e. The targets in the sliding mode control is to make the sliding function equal to 0. So we have changed our mathematical equations into one function, which I call it the sliding function or the sliding manifold, that is equal to e dot plus c equal to 0. So if you look at this equation, you can see that we have changed the order of the system from a second order to a first order system. So we have reduced the order of the system. It means that we have simplified the system. This is one of the most important characteristics of the sliding function, that we are simplifying the system. The second thing, that when you look at this function or the sliding function, you can see that s is equal to e dot plus ce. It is only dependent to the error and a constant coefficient, and it is not dependent to the parameters of the system. That's why we say that the sliding method is robust. It means that it is not dependent to the parameters of the system. So what is the next step for the sliding mode control method? After defining the sliding function, we need the derivative of the sliding function. When the sliding function becomes 0 in a steady state, the derivative of the sliding function should be also equal to 0. So right now, my target is to take all of the variables into this sliding line, which is equal to 0, or a sliding function. What should I do? I should design a relay control that will take all of those variables into the sliding line and make them 0. This relay control, the conventional relay control, is such a function, which we call it a sine function. U is equal to u naught sine of e. So how it is working? This sine function is a discontinuous control input. It is working like this. If I consider that the sine is a function of the error, then when the error is positive, u is u naught, and when error is negative, u is minus u naught. So when I have such a sine function, sometimes it is positive, sometimes it is negative, it takes the error as the input and gives the control input as the output of the relay control. This input of this sine function can be error or it can be the sliding function. Both of them can be used. If the sliding function is equal to e, so our input is e. If the sliding function is equal to e dot plus ce, so the control input is s. So if I want to summarize those two steps in this figure for making it much more clear, you can look at this figure. First of all, I will design the sliding function for my system. If the order of your system is second order, then the sliding function is something like this. CE plus E dot, it should be equal to 0. If I say that the sliding mode control is happening and the sliding function is equal to 0, then we have a first order differential equation. If you solve this first order differential equation, then it is such a red line in this E dot plane. The slope of this red line is equal to C, or this coefficient that I call it the sliding mode coefficient. Then the second step is that we should take all of the variables or the dynamic of the system from its initial point to the sliding function or to the 0 value. How we can do it? We will design the control rule. Let us say that the control rule is a conventional control rule, and it is U equal to U naught sine of S, a signification function. So when I apply this control input to the system, such a movement or such a motion will happen. What is this motion? First of all of our state variables will move from the initial points anywhere in the plane. They will move from their initial point to the sliding function. Then after some zigzag movements that you can see here, the gray line, after some zigzag movements, they will reach to the sliding function and S will be equal to 0. So in a sliding mode control, we have two phases. First, we have the reaching phase, and second, we have the sliding phase. If you look at these zigzag movements that I have bounded with two blue lines, which it has a bounded magnitude, this is what we call it chattering that is happening in the sliding mode control method. So right now there is a question here. How it is happening, how this control rule will help us to take all of the state variables from their initial points to the sliding surface and then keep them around the sliding line and keep them sliding on this manifold. It is the stability analysis. There is an stability analysis. It should happen for all the control methods, and it will guarantee that your system is stabilized and it is sliding on the line. What is this stability analysis? S times S dot should be less than minus eta magnitude of S. Eta magnitude of S is saying that it is a very large magnitude, positive magnitude. What does it say? It is saying that S times S dot should be less than a very large negative value. I will talk about it later on, about this stability analysis and how it will work. But there is another important thing that you will see in literature about the sliding mode control, and it is the equivalent control. There is another control input that we call it equivalent control input. The equivalent control input can be found by making the derivative of S equal to 0. When the system is on the sliding mode, it means that we are on the sliding phase and the system is working. It means that S dot is equal to 0. So in such a situation, we have an equivalent control. If we give this equivalent control as the input to the system plus this sign control, then the reaching phase will decrease. So it is helpful to use the equivalent control. It will decrease the reaching phase time delay. But sometimes it will also complicate the control input. Why? Because when you find the equivalent control, it uses some parameters of the system. So it is an optimization method that if you need this equivalent control or you do not need. If the system is working good, it has a fast response. Without equivalent control, it is better only to use this switching control input. So let us talk about the stability analysis. What is the stability analysis and how it is helpful for designing the sliding mode control? Maybe You ask that, do we need this stability analysis whenever we design the sliding function? Of course, we need it. Because you see that we have some constant coefficient of the sliding function, and for finding the optimum value for this gain, we need the stability analysis. So I think that we can see the stability analysis for this mathematical equation. Let us consider that we have an error, and the error is y minus y reference. You know that y is equal to x based on the mathematical equation that I have given before. So if I find the derivative of e, we have y dot minus y dot ref, and it is equal to x dot minus y dot ref. So I can say that the derivative of s is equal to e double dot plus c e dot, and it should be equal to 0. So if I find derivative of s, it is equal to second derivative of e. The second derivative of e can be found from this equation, second derivative of x minus second derivative of y plus c e dot. You can substitute the values from the equation. For example, second derivative of x is f plus g times u minus y double dot ref plus c dot c e dot. So what is the stability analysis? We will use a Lyapunov function for proving the stability of the system. It is saying that you should find a function that we call it a Lyapunov function, which is a strictly positive function. So for choosing this function is arbitrary. You can find what function you like, but it should be a strictly positive function. 1 over 2 s squared is a strictly positive function. So the Lyapunov stability analysis says that for the sliding mode control existence, you should prove that the derivative of this Lyapunov function is strictly negative, or it is strictly less than a negative value. What is this negative value? Minus eta magnitude of s. So in this situation that the Lyapunov function is 1 over 2 s squared, v dot is s dot, it should be less than minus eta absolute s. And eta is a large constant value, and it should be positive. So for this example, let us find s dot. We have two situations, when s is positive and when s is negative. If s is positive, so the control input, which is sine, is positive, so u is equal to u naught. But when s is negative, u is equal to minus u naught. So for different cases, we should analyze the system separately. When u is equal to u naught, we will find s dot, and when u is minus u naught, again we will find s dot. So for each situation, we will have an inequality. S dot should be less than minus eta magnitude of s. Again, for the second situation, we have s dot less than minus eta magnitude of s. I will prove the first one. I will show you how you will use it to find this coefficient. And for the second one, it is same as the first one. You can do it yourself. So let us go for the first one. The first one is saying that s dot, which is this function, should be less than minus eta magnitude of s. How we can prove it? Instead of s dot, I can substitute this value that I had found before, fx plus gx u, but instead of u we have u naught minus y double dot ref plus c e dot. So right now let us look at here. If you remember before, I told you that we do not know anything about f and g. And in a sliding mode control, it is not important to know about it, because the sliding mode control can work under uncertainty. But the bound or the limit of f and g is important for us. So I can say that it is less than f of x plus g of x u naught minus y double dot ref plus c e dot, we know that S is less than magnitude of S. So I can substitute this value. Then I can say that this new term, which is fx plus gx u naught minus y double dot ref plus c e dot times magnitude of S, is less than the bound of f and g. What are the bound of f and g? Instead of fx, you can substitute f naught. Instead of g, you can substitute g naught. So now we have simplified our inequality. It means that f naught plus g naught u naught minus y double dot ref plus c e dot is less than minus eta magnitude of S. So right now you have a simpler inequality, and you can find the limits of the coefficient of the sliding gain. When you solve this inequality and you find the boundary for the C, what it is telling you? It is telling you that if you want to select the constant of the sliding function, you should consider this inequality. You should satisfy this inequality to the sliding function, then the sliding mode will happen, and the other things will happen, and you can control your output. So after talking about the sliding mode control, and you are familiar with the sliding mode control in a very simple method, and it was a conventional sliding mode control, right now I want to tell you why it is interesting to use sliding mode control for power electronic converters, and why we are using it. Let us clarify with a power electronic converter, which is a rectifier. Rectifier means a power electronic converter that is changing AC into DC. So the input voltage is AC and the output voltage is DC. Let us first of all look at this power electronic converter. As you can see here, we have 4 switches. It is an H bridge. When S1A and S2B are closed, then the input voltage of the H bridge is equal to output, and when S1B and S2A are closed, the input voltage of the H bridge is minus V out. So I can show it like this. I can show the input voltage of the H bridge as U V out. What does it mean? It means that when U is equal to 1, we have V out. When U is equal to minus 1, we have minus V out. So if you look at the control input or U of this system, it is a 1 minus 1 control input. So I can say that the power electronic converters are variable structure systems. Why? Because this structure of the switches are changing. So it is very similar to the idea of the sliding mode control. If you remember, the control input of the sliding mode control was also a sine function. It means that it is generating 1 and minus 1. If you remember, for example, if the error is positive, it is generating 1. If the error is negative, it is generating minus 1. So if you compare the sine function, which is the relay control of the sliding mode control, and compare it with the control input of a power electronic converter, you can see that both of them are similar. That's why I can say that a sliding mode control is an appropriate control method for power electronic converters. It means that directly I can apply this relay control to the switches, and the power electronic converter will work very easily. That's why we like to use sliding mode control for power electronic converters. So we have such a point of view that based on what I explained, we have such advantages for the sliding mode control. We have robustness. It means that our control method is not dependent to the parameters. Even if you change the parameters, nothing will happen. Your control method will work efficiently. The second thing is that it reduces the order of the system. It has fast dynamic response. It is very simple. It has very easy implementation. So I can say that it is a promising method to control high-order, nonlinear systems that are operating under uncertainty and also when we have disturbances. But there is another important thing about the sliding mode control that I also talked about it, and it is the disadvantages of this sliding mode control. It is the first one is the chattering. I talked about the chattering, the zigzag movements that we had seen before. When the state variables are moving from the initial point and then they are coming to the sliding function or a sliding line, they are not becoming completely zero, but they are sliding around the sliding function, and you can see such a zigzag movements. It has finite frequency, finite amplitude oscillations, and it is coming. Why it is happening? If we have an ideal system, it will not happen. But because you know that the mathematical modeling of the system is different from the real system, that's why we have some unmodeled dynamics in our control loop. So we have this chattering. So why we do not like chattering? Why it is a disadvantage? Because it is resulting variable frequency, and variable frequency is an unwanted situation. The second problem of the conventional sliding function is that when you want to select the sliding function, it should be selected in such a way that the derivative of s should be directly dependent to control input u. This is what we call it relative degree 1. It means that when you want to design the conventional sliding function, the relative degree should be equal to 1. It will also make some problems in the system. There are a lot of methods in the literature that are addressing this problem. For example, they use nonlinear sliding functions such as terminal sliding mode control or high-order sliding mode control methods. The third disadvantage is that most of the studies that right now we are doing are based on continuous sliding mode control. And as you know, right now we are using digital systems, and we like to experimentally work on these power electronic converters. We are using digital systems, so we need to have sufficient studies on discrete sliding mode control, and it can be also a future work. So I like to talk about this chattering problem because it is a very important problem in the sliding mode control. This chattering alleviation has been the research topic for a lot of papers and articles. If you look at this recent paper that is talking about the sliding mode control overview and its application in power electronic converters, it is talking about the chattering alleviation methods. There are a lot of methods, but the most important methods are these 4 methods: hysteresis function method, boundary layer method, state observer method, and super twisting algorithm method. They are methods that we use for solving the chattering problem that is existing in a sliding mode control method. If we look at the hysteresis method, it is a kind of method that we use for decreasing the chattering. How is this method? This method is bounding the sliding function in a boundary to decrease the magnitude of chattering. So if you look at the block diagram of this control input, when you design the sliding function, then you will apply this hysteresis bound, and you will not apply this control input directly to your power electronic converter. So it has an easy implementation, but however, again, it has time varying switching frequency, and it has a steady state error because the band of the hysteresis has a very important characteristic. If you do not choose it properly, the steady state error can exist. There is a second method that we are using for solving the phenomena of the chattering. We call it boundary layer. How the boundary layer is working? The boundary layer is concentrating on the control input. If you remember, the control input was a sine function, so it was a discontinuous function, suddenly changing from -1 to 1, and it was making such a chattering. So the boundary layer is saying that instead of that that discontinuous control input, you can consider a boundary, for example, from minus phi to phi. You can consider a boundary for S, and in this boundary, the control input will be linear. So if we consider such a boundary and make our sliding function linear, then we can apply this sliding function directly to the power electronic converter by a PWM. When we can use the SPWM in the system, it means that we have easy implementation, the switching frequency is fixed, but again, same as before, we will have the problem of a steady state error. Why we have the problem of a steady state error? Because again, in the boundary layer method, the system is dependent to the boundary layer value that you can see in this figure. It is shown by phi. If you do not select the value of phi properly, a steady state error will exist. Finding the phi is also very difficult based on try and error. This parameter selection has a lot of difficulties. So there is a third method you can see in the state of the art. It is the state observer. A state observer works based on an observer. It is not using directly the state variables. It is not sensing the state variables. It is using some observers. When you use another loop, which is the loop of the observers, because the main loop has to track the observer loop, the chattering is somehow alleviated. It has some flexibility because it is alleviating the chattering. It cannot completely remove the chattering. It has complicated implementation and requires more effort in the control design. And finally, we go to the super twisting algorithm. Super twisting algorithm is suitable for the systems that has relative degree 1. So again, I should mention here that however second order sliding mode control or high order sliding mode controls can be used for high order relative degrees, but super twisting algorithm can be used only for the systems with relative degree 1. But on the other hand, it will solve the chattering problem. The discontinuous control input will change to a continuous control input. So we can apply it directly to PWM, and we can have a fixed switching frequency. The problem about the super twisting algorithm is that the stability analysis of the super twisting algorithm is very difficult for the power electronic converters, and we do not have comprehensive theoretical proof. So after talking about all of these methods, talking about the chattering alleviation, right now I can go through the applications. I want to talk about some different converters, and then we will talk about how to apply the sliding mode control method for these converters. This sliding mode control method, the conventional one, and also all of the modifications that have been applied on the sliding function, applied on the control input, applied on the modulation method, all of them are in the state of the art. You can check them from the literature review. This sliding mode control has been applied on DC-DC converters, DC-AC inverters, AC-DC rectifiers, AC-AC matrix converters, and also on active power filters, for example, such as DVR, STATCOM, and a lot of in power systems. You can check them. I want to start from a very simple DC-DC converter for clarifying how to use the sliding mode control method, how it is going, how I go through the processes. It is a buck converter. You know that buck converter is a converter that gets a DC voltage as the input and gives a DC voltage as the output. The output voltage is always less than the input voltage. We have an LC filter and we have a switch. As you can see, the switch has two positions. Sometimes it is 1, sometimes it is 0. So you have 0 and 1. How can I apply a sliding mode control to this system? If you remember in the introduction part, when I was talking about the sliding mode control, I talked about a sine function that it can be 1 minus 1. Let us somehow rearrange that sine function. If I change the sine function into this value, which is u equal to 1 over 2, 1 minus sine of s. You can see that if s is positive or more than 0, u is equal to 0, and when s is less than 0, u is equal to 1. So if I define such a control input for my sliding function, then I can find 0 and 1. So right now it is very simple to use the sliding mode control. First of all, I should tell you, for finding the sliding mode control, I mean for designing the sliding function, for designing the control input, you do not need the mathematical equation of the system. You do not need the parameters of the system. That's why the sliding mode control is very simple. It is very easy to be implemented. But for the stability analysis, we need the mathematical model of the system. That's why I will go through the mathematical model of the system. So for designing the control method, first of all, let us look at our target. What is the target? My target is to control the output voltage. So for such a target, I will define two state variables, x1 and x2. x1 is the inductor current, x2 is the output voltage. If you go through the mathematical model of the system and find the state space equations, we have x.1 and x.2. Then let us also find x2 double dot, or the second derivative of x2, substitute x.1 from the first equation, and finally you go through this final equation, which is showing that second derivative of x2 is equal to a function of x2, u, and x dot 2. As you can see, this equation is a second order equation. x2 is output voltage, so we can say that the degree of our equation is 2, or r is equal to 2. If you remember, for designing the sliding function, the conventional sliding function, k should be equal to r minus 1. So k is equal to 2 minus 1, which is equal to 1. So I want to design the sliding function. S is equal to d over dt plus c to the power of k, which is equal to 1 times e. So I have designed the sliding function. It is e dot plus ce. When you look at the sliding function, you can see that for designing this control method, you only need to find the error and find a constant value. So we will not work with L, we will not work with C, we will not work with R, and we will not work with the mathematical equation and the disturbances that are happening in the system. For example, the disturbances that we have in VS, the disturbances that we have in the load. That's why we call the sliding mode control a robust control method. So the control input has been assigned before. It is 1 over 2, 1 minus sine s. And then you will apply this control input directly to this switch without using any modulation method. So what will happen if you simulate, for example, this model in MATLAB? The results are here. For example, if I consider that the reference of my output voltage is 5 volts, you can see that it will start from an initial point, and then the output voltage will track the reference. I have shown you another figure here that shows E dot versus E. This is the plane of E dot and E. You can see the motion of a sliding mode control. It starts from an initial point and then goes through 0 point, which we call it equilibrium point, and it will reach the equilibrium point. If you want to decrease this reaching phase, you can increase the value of C. But if you decrease the value of C, the reaching phase will last longer. How can you find the optimized value for C? You should find the stability analysis of S dot less than minus eta magnitude of S. So after this simple simple buck converter, let us go to another application, which is the grid type LCL filter inverter. This subject is coming from this paper that you can go through all the mathematical equations, all of the ideas if you need much more results. As you can see, this is a very simple inverter, single phase inverter. It is connected to the grid via an LCL filter. In an LCL filter, you know that the most important problem is the resonance that is happening between inductors and the capacitor. So when we want to design the controller method, we should consider our target, and also we should consider the resonance damping. So what is the target? The target is to tune the capacitor voltage and tune the grid current that I have shown with red circles. So I will define three state variables, x1, x2, and x3. x1 is the capacitor voltage error, x2 is the derivative of capacitor voltage error, and x3 is the inductor current error, or the grid, let me call it the grid current error. So look at the sliding function. It is a linear sliding function, but there is a new idea in this sliding function. What is this new idea? If you look at the first and second term, alpha x1 plus x2, it is same as before. The sliding function that I talked about, you have the error times gain, which is alpha, plus derivative of error. But you have a new function here, which is beta x3. So we have a new gain. This new gain is beta, and you have x3. x3 is the error of the current, but on the other hand, it is the integral of the first state variable. So this is what I can call it integral sliding mode control. So it is the contribution of this paper, this sliding function, and also it is using the conventional control input, a sine function, sine of s. There is another contribution in this paper that it is using a double band hysteresis scheme instead of injecting this control input directly to this power electronic converter. So if you look at this figure, you can see how the hysteresis function is working, how it is generating the control input. Then by using the stability analysis of the Lyapunov function, you can optimize the values of alpha and beta that you can see in this figure. This paper is optimizing the values of alpha and beta in such a way to have an existence region for S, the highest existence region when S is positive and S is negative. If you look at the results of this paper, you can see that under event disturbances, for example, when the grid current is changing, again in a very fast time, the system is working. But what is the disadvantage of this paper is that it is working under variable frequency. This is the switching frequency of the system. You can see that it has variable switching frequency. For solving this variable switching frequency in another paper, we have proposed a boundary layer method. This boundary layer method is used in an standalone quasi-Z source inverter. Quasi-Z source inverter is a kind of inverter that is using a quasi-Z source after the DC input voltage. If you do not have enough information about the quasi-Z source, you can go through this paper and find some ideas about the quasi-Z source, how is the modulation method of this system. But for working on the sliding mode control for such an inverter, I should go through the control method that we have, or we need two sliding functions. For the DC side, we need a sliding function, and for DC side, for AC side, we need a sliding function. In a quasi-Z source inverter, we have two situations. These two situations are the shoot-through state and non-shoot-through state. When we have shoot-through state, the input voltage is 0. When we have non-shoot-through state, the input voltage of the H-bridge has a value. So I can say that it is a challenging power electronic converter. Why? Because our input voltage is not a constant value. It is like a pulse, because the input voltage, or VPN, is a pulse. So let us go through controlling this system. First of all, we go through the mathematical model of this system. For finding the mathematical model, I have given them. We have two equations for DC side and one equation for AC side. Then we have three state variables, x1, x2, and x3. First and second state variables are the errors of DC side, inductor and capacitor. The third state variable is for the AC side. So we have two sliding functions, DC side sliding function and AC side sliding function. The DC side sliding function has a gain, but the AC side doesn't have. So what is the contribution of this paper? It is about the control input. As you see, the control input, if it was a conventional control input, we should have used such sign functions. But instead of using such sign functions, we are using boundary layer method. In boundary layer method, I told you that we will consider a boundary for the sliding function, and in this boundary, the sliding function is linear. When in this boundary, then the sliding function is linear, then we can use a PWM, and the system will work with fixed switching frequency. The control method of this system is given in this figure. You can see that we have a very simple sliding function and control input for DC side, the control input and the sliding function for AC side. And finally, you can see the results. The inductor current, the capacitor voltages, all of them are tracking their reference. The output voltage and output current are also tracking the references. And on the other hand, the switching frequency is fixed. There is another method that I would like to talk about, and that we are using for power electronic converters. It is solving some problems about the boundary layer method. As I told you, the boundary layer method suffers from a problem. The problem is coming from that boundary. When we change the value of that boundary width, an SCD state error is always existing in the system. So instead of using that boundary layer method, we prefer to use super twisting sliding mode control. The super twisting sliding mode control is working or modifying on the control input. Instead of the sign function, we will use such a function. It has two terms. We can find some similarities between the super twisting sliding mode control and the PI controller. You know that PI controller is a linear controller, and it has two terms, the proportional part and the integral part. In the super twisting controller, also we have two parts. However, it is a non-linear controller. In the proportional non-linear part, we have roots of the sliding function times sine of s, and in the second term, we have integral of sine of s. Because of using integral of s, we are making this control input continuous. There are also two papers that are here. You can go to these papers to see more detail about the super twisting sliding mode control, but I will give you some information about them. First one is a grid-tied quasi-Z source inverter that is using super twisting sliding mode control instead of the conventional ones. If you look at this quasi-Z source inverter, it is connected to the grid via an LCL filter. So we have a lot of challenges in this system. First challenge is that we are using a quasi-Z source inverter. It means that our output voltage is a pulse. Our input voltage, which is VPN, is a pulse. The second thing is that we are using LCL filter, so we need resonance damping. The third problem is that the grid side, or VG, has harmonics. This paper is using a grid that is distorted by harmonics. So we want to solve all of these problems by using a sliding mode control method, which is using the super twisting control input. So we have defined three state variables, x1, x2, and x3, again same as before, but the difference is that x3 is the capacitor voltage instead of the current. So again, we have two sliding functions, alpha x1 plus x2, beta x3 plus x dot 3. If you look at the block diagram of the control method, it has two separate parts. First part is the DC part that I have found SDC. It is very simple to find SDC. And the second part is the AC side. The AC side has some other control parts. They are used for decreasing or for removing the distortions of the grid. And then I will apply the sliding function. Here, the point of the super twisting sliding mode control is here, that instead of using the conventional sine function, I will use the super twisting sliding mode control for both DC side and AC side. If you look at the super twisting sliding mode control rule, it has two gains, lambda 1 and lambda 2. So we should define these lambda 1 and lambda 2. For finding lambda 1 and lambda 2, two methods are existing right now. The first one is try and error. It is time-taking, it is tiresome. And the second one is to use the stability analysis. And as I told you, there are a lot of difficulties in the stability analysis. So, however, after finding these control inputs, we can apply them to the PWM and we can achieve a fixed switching frequency. So let me show you how is the result and how the results are interesting. If we use the conventional sine function, you can see the control inputs because they are sine function, they are discontinuous pulses, and you can see the chattering. But if we use the super twisting sliding mode control, you can see the AC side, we have approximately a sinusoidal function, and in DC side, we have a constant value. That's why we have a fixed switching frequency, and approximately we can say that we have removed the chattering. So if you look at another result of this paper, you can see that however the grid voltage is under distortion, and you know that we have LCL filter, we should have used a resonance damping, but by using the sliding mode control method, you can see that we are having a grid current which is sinusoidal and free of harmonics. Also, I have another example for the super twisting sliding mode control, but right now it is somehow different because I have used the super twisting sliding mode control also for observing a variable. I have used in a dual active bridge converter. The dual active bridge converter is a popular DC-DC converter. It is using an isolation transformer, and it is working based on the phase shift between the inverters or the half bridge in rectifier. One of them is rectifier, one of them is inverter. So here I want to, my target is to control the output voltage. So very simple sliding function. My sliding function is equal to V out minus V out star. Then I will use two control inputs. One of the control inputs is the equivalent control input, and the other one is the switching control input. As I told you, sometimes you can use the equivalent control input, sometimes you cannot. But right now, for improving the time response, I have used this equivalent control input. If you look at the equivalent control input, it is a function of the load current. So, because the load current is not accessible, I do not like to sense it directly. I prefer to use an observer method. What kind of observer? I will use a super twisting sliding mode current observer to estimate the load current. So how it is possible? Here, I will find a mathematical model of the load side. This mathematical model is using the output voltage and load currents. If you look at this mathematical model, it has two switching rules, and both of them are using super twisting rules. So if we define a new sliding function for the observer and call it sigma, sigma is the error between the observed voltage and the real voltage. And then we give this sigma to the control inputs or switching control inputs, and the result is the observed load current. Then we can give this observed load current to our original control input, which is U, and it will be applied to PWM, and it will generate the switching pulses. So let us see how this method is also working. If I show you the load current, the output voltage, and the control input, you can see that even under the load disturbances, the output voltage is stable on the reference, which is 400 volts. And also you can see the control input, which doesn't have any chattering, and it is changing based on the disturbances. The second thing that I like to show you, it is the capability of the observer, how it is working. The blue one is the real load current, and the red one is the estimated load current. As you can see, when we have some disturbances, it takes some time, for example, to again track the value, but in a steady state, it has a zero steady state error. So what if we use the conventional sliding mode observer instead of super twisting sliding mode observer? If I compare them to each other, it has also interesting results. If I use conventional sliding mode observer, when we have a disturbances in the system, it has very fast time response, on the contrary to super twisting. But you can see that it is suffering from chattering. So what should we do? We should go through an optimization. Optimization between the conventional sliding mode control and super twisting sliding mode control. Which one is better for our application? So I can say that all of these are the applications, or a summary of the applications that we can use for the sliding mode controls. If you need much more information, you can go through the literatures and the state of the art, much more modifications about the sliding mode control. But in the conclusion, I can tell you that the sliding mode control method is a proper method for power electronic converters. However, it is suffering from the chattering problem, but the chattering problem can be solved by new methods. And for the future work, I can suggest the students or the people who are eager to work on the sliding mode control that they can work on the discrete sliding mode control methods. So thanks for your attention. And thanks for joining this presentation. And I enjoyed talking in this presentation. Thanks from the people from the IEEE Young Professionals Power and Energy Society to give me time to talk about my field of study. Thank you.
Thank you, Professor. So we can ask if someone has questions, they can ask, they can write it. If anyone has a question,
if there is any question or something.
Any question related to the topic are welcome.
Thank you. Thank you, Professor.
Anyone have a question, they can type it. I will ask my question about conventional mode optimization. Can you talk about it a little?
Talk about?
Conventional mode optimization.
I didn't hear.
Conventional mode optimization. The optimization of conventional mode.
Would you please write your question because your
Oh, you don't hear me?
the optimization of
A conventional mode.
the application.
Optimization of conventional mode.
Sorry that I cannot hear your.
Oh, I typed it. Can you check it?
Okay, optimization of conventional mode. So there. Yes, I could right now. I could because your sound was not good. So let me open my file and talk about the optimization of conventional mode control. Okay, here we can call this paper a kind of optimization method for the conventional sliding mode control method. As you can see, the control input is considered U equal to minus sine of S. So when we want to find the gains alpha and beta, when you go through the stability analysis for finding the alpha and beta, it has a very large area for finding these values. So how we can go through these values, how we can move through these values, and how we can optimize these values. This paper is finding the values of alpha and beta based on the errors that are existing in the system. So it is using such a plane x1 and x2. And then it is considering different situations that can happen for the sliding function and its derivative in this region. And then applies some disturbances to the system and considers that what is happening in these regions. So I can say that based on mathematical equations, they are optimizing the values of alpha and beta. So they will, for example, apply values for x1. So they will find a line E1. Then they will apply the disturbances. They will find line E2. And they are moving inside this region and find variables of a sliding function. Then they will try which value is better, is giving better stability, it is giving less steady state error, and they are moving in this region. And by some kind of mathematical equations and graphical theories, they will optimize these values alpha and beta. This is the optimization method.
Thank you very much. I got it.
You're welcome. You're welcome. Thank you.
I guess there are no questions from the audience. If anyone have questions, they can type it.
Okay, if right now you do not have any questions, but if someone is also here, has any other questions, they can get in contact with me by my email. I welcome any questions even in my email. I can talk about sliding of control. Even if there is any kind of teamwork, I appreciate it. They can keep in touch with my email. We can talk about sliding of control method.
Okay, thank you very much, Professor Farzaneh Bagheri, for joining us. And this was a very fruitful session. And hopefully that in future we will organize another events and many other professors, and you can also join us. And thank you everyone for joining us today, and stay tuned for our future events. Thank you very much.